Let's do it.
All righty. All right, everyone. I am here with Abhishek Gupta. Abhishek is a Ph.D. student at UC Berkeley, where he works with folks like Peter Abil and Sergey Levine, who we've had on the show before. Abhishek, welcome to the TWiML AI podcast.
Thanks, Sam.
Looking forward to digging in and learning more about your work and your background. What got you interested in studying RL and robotics?
Yeah, so I think my first experience with robotics was actually this first Lego League type competitions where we would like make these little Lego robots and they would like do these challenges. And when we first did it, we made the robots just by hard coding all the different primitives and programs to do everything. And that works to some extent, but I think when I came to Berkeley, it was really exciting to see that people had more sophisticated techniques to control robots. It was also the only thing that I'd ever done before then in terms of project experience. And so I reached out to a number of professors because I thought their projects were cool. And Peter specifically had a lot of research at that time on folding laundry and flying helicopters. And I was like, wow, this is really amazing. So I'd reached out to him as a freshman. And then he hired me as an assistant in his lab to kind of help out with some software engineering projects and some research projects, and kind of got started on research from there.
Awesome.
And so then, like, the first set of experiences that I had there were kind of like helping grad students and postdocs on their research projects, which were largely related to folding laundry and tying knots and folding towels and things that Peter was excited about at the time. And from there, I think, like, in grad school, my research and interest transitioned a lot more towards reinforcement learning and learning-based ideas.
Cool. So within that kind of broad scope of RL and RL for robotics, and I guess maybe that's broad from a TWiML perspective, since we've had a bunch of conversations on that. Where do you focus? Like, what are your research interests within those fields?
Yeah. So I guess since I'm a person who's really excited about robotics and I want to get robots to work because I think they have a lot of impact. And I see RL as a great tool to enable robotics, more so than exploring RL for the sake of RL. And so what I specifically think about a lot is, like, what are the things that prevent us from applying reinforcement learning to robotics problems in the real world. So, for instance, if we want a robot to like operate in a kitchen and clean up your kitchen or make a meal, what is it that's preventing the algorithms that work on AlphaGo, AlphaStar, whatever, from being applied to these types of systems? And so I specifically think about, like, there's a mismatch in assumptions between what these algorithms typically assume and what's actually available in the real world. And so I kind of think about how do we bridge these mismatched assumptions. So specifically, what I mean by that is for instance, in a game or in a video game or a board game, you'd assume that the score is provided, so the reward function is really easily available. But in the real world, there's no score which tells you what you're doing, right? Or, for instance, in a video game, you can collect millions of samples. But in a physical robot, if you do that with random exploration, you're going to either break yourself or the environment. And then also, just like, there's a lot of assumptions that we make where we can hide our dirty laundry in simulation, so we can like reset to wherever we want, or we can like magically set the state of the world in some ways. And a lot of our algorithms are critically reliant on these assumptions, but in the real world, you just can't do that. And so kind of been thinking about how do we bridge these mismatched assumptions in that way. So
are the problems that are most interesting to you the ones that you mentioned earlier that you kind of cut your teeth on with Peter and Sergey, like folding laundry and knot tying and that kind of thing? Or do you have some other, do you have when you think about your work, do you have some set of canonical problems that come to mind?
Yeah, that's a great question. So I think it would be great if we could fold our laundry and tie our knots and do the things that we used to do, but I don't think we're quite there yet. So I think we're still getting objects to be pushed around and picked up, and more basic skills before we can get to the more complex ones, right? So there's like Moravich's paradox, which indicates that like learning low level skills can often be harder than learning the higher level ones, and I think we're kind of stuck in that regime. But we're making a lot of progress, I think.
Mm-hmm.
But yeah, so specifically to kind of like dive in a little more into like specific research interests that I've been thinking about a lot. I think a lot about reward supervision and how do we provide rewards in the real world. I think a lot about how we can get data collection to be efficient and safe. So how do we bring down sample efficiency, and how do we get it to be much more directed in exploration? And lastly, I think about how to make large-scale continual learning systems which can keep collecting data without humans interfering all the time, so that we can like scale data collection to many, many hours and many, many days of collection.
When you think about reward supervision, what are the ways that you've approached that problem?
Yeah. So I kind of like try to think about how we can provide rewards in as natural a way as possible. And so normally what people do right now is they program a reward function by hand, and I've tried to move it more towards either providing weaker forms of supervision or learning from no supervision at all. And so one line of work we had was on how do we get reward functions to be learned from raw videos of humans performing tasks. So we have video demonstrations of humans performing tasks in different scenarios. Can we take those, extract reward functions, and use those to have robots learn as well? And then going from there, we kind of like tried to make the supervision even weaker. So we said, can we like try and learn from just images of successful outcomes rather than entire videos? Or can we like learn from natural language supervision instead of entire videos or images? And then if you take this to its complete logical extreme, we thought of like, can we learn without any reward supervision at all? So we just drop a robot into an environment completely unsupervised and say, can we learn skills without reward functions at all? And we were kind of trying to explore that paradigm.
So those all sound like really interesting experiments. Like walk us through, how far you got with each.
Yeah. So maybe you can start with learning from raw video, and I think that one is particularly intuitive, because we often think of babies watching their parents performing tasks, and they're able to infer the intent behind the task from these types of observations, and they're able to use that inferred intent to supervise themselves practicing the task in order to like learn how to do it. And so what we try to do is take video demonstrations, which are just sequences of images without any actions or states provided, and say, how can we extract rewards to get RL to work, especially when these videos are coming from different viewpoints. So imagine if you were collecting data off the web or something, these videos might be from different viewpoints, different lighting conditions, different backgrounds, so completely different in context. And in that case, the problem of understanding what's happening in these videos becomes even more difficult. And so that's kind of the problem setting we were thinking about. And the way we kind of approached it is we try to explicitly learn a model that imagines what an expert would do in the robot's context. So we said that, okay, if the robot is in a new scenario, let's try and learn a model which is able to predict what the expert videos would be in the context of the robot. And once you're able to imagine what the expert videos look like in your context, then you just try to match your own behavior to those expert videos. Right? And so we trained a translation model that translates between these different videos and viewpoints and figures out what the expert would have done in your scenario. And then we try and match the behavior in terms of the image observations with what the predicted behavior would be. And what that allows... Sorry, go ahead.
What's the thinking behind introducing the expert into the model beyond just kind of predicting the behavior?
So do you mean what's the rationale behind having the expert supervise the system at all?
Exactly.
Yeah, so I think when you're trying to get goal-directed behavior, you need to have some indication of what problem is being solved and all, right?
Mm-hmm.
And so in that sense, we need some semantic information of what the task is that is being solved. And a particularly natural and easy way for a human to provide that is just by recording themselves performing the task, right? And so it's an extremely easy way to like convey a lot of information about what the problem is that is being solved. And so that's kind of the rationale for having the experts involved.
Mm-hmm.
And so what? Sorry, go for it.
Sorry, the videos that you're using in these tasks, are these explicitly recorded for your problem, or are you pulling them off of YouTube and they're not specifically recorded for this task?
Yeah, so I think it would be great if you could pull them off YouTube, but I think we have some more work to go to get there. So in this setting, we recorded them specifically for this problem, but we recorded them without much like specific care in terms of fixing the viewpoint or fixing the object positions. It was kind of more random. And the tasks we considered were things like sweeping granular media or pouring things with almonds. So they're actually really hard to provide reward functions for in any other way, because you have to like either track every single almond which is in the scene and provide a reward function for it, or you have to come up with an instrumentation system where you put a marker on every object.
Mm-hmm.
And in those cases, just providing a single video of doing the task is a lot easier to do. And so the motivation was like, there's no other way to supervise those systems. And so learning from video is the easiest way to do that.
Mm-hmm. Interesting. Yeah, it reminds me a bit of the imitation learning work that Nando De Freitas and folks are doing at DeepMind. Some of that was direct off of YouTube videos, but I think they were playing video games as opposed to trying to make a robot, manipulate things in the real world.
And I think that introduces a particularly different challenge, which is that when you're playing a video game, you're doing it in the embodiment of the system, right? You're doing it in exactly the same frame viewpoint. You're doing it with the same controls. You have everything the same. Whereas when a robot is doing things versus a human is doing things, there's an embodiment shift. There's a shift in how the tasks are being performed. The viewpoints are different. Like a lot of those contexts are not the same. And I think that it adds a level of difficulty which requires all of this extra machinery to deal with.
Yeah.
I think one thing that they did, which was kind of cool, was they also used audio when they were learning from these YouTube videos, and they like synced the audio and video. And I think that'd be pretty cool to explore as well.
Mm-hmm. So you kind of started out with this spectrum of, starting with video and getting to simpler and simpler forms of supervision, ultimately to no supervision.
Yeah.
What's the next step in that continuum?
So I think really pushing the no supervision paradigm a lot further, I think is going to be really imperative. So specifically, the scenario that we're thinking about is where you like take a robot, you drop it into an environment, you don't tell it what it's doing, but you just let it explore the environment on its own for many, many hours. And then someone comes in and says, okay, well, try and do this particular task. And you can now use all of that experience that you've collected in order to learn that task a lot quicker, right? And I think that given that we're starting to deploy so many robots at scale, like being able to supervise or being able to have them run unsupervised for really long periods is going to be really impactful in terms of scaling up robotic learning. And so specifically, the stuff we thought about there was how do we do unsupervised skill discovery, which is how do we learn behaviors when no reward functions are provided. And if no reward functions are provided, it's not really clear what to optimize for.
Yeah.
And what we did there was we optimized for diversity, which says that you want to optimize for behaviors that are as diverse as possible. And if you can optimize for behaviors that are as diverse as possible, the idea is you can cover the space of all possible behaviors so that you're as well prepared for the future as possible. And so you can provably show that if you optimize for this diversity type objective, then it best prepares you for the future when you assume the worst case. And so I think that we've had some preliminary results in simulation where we've been able to control, little simulated characters to explore the world in surprising ways. You can get them to do backflips and front flips and run without any reward functions. But really pushing it to a real system, I think, requires a bit more work.
Mm-hmm. How does this idea of encouraging diversity in behaviors in your system compare or contrast to like turning reward all the way up in your reward I'm sorry, not reward, explore all the way up in your explore exploit, or other approaches that kind of optimize for novelty, that kind of thing?
Yeah, that's a great question. So I think the difference between unsupervised skill discovery and exploration is that exploration is in many ways undirected. So exploration is just going to say, let's try and visit all of the states that we can. Whereas unsupervised skill discovery is directed in each skill, but it's overall trying to cover the entire space. So every skill itself is repeatable and goal directed, but the overall set of skills spans the entire space. So the useful thing about unsupervised skill discovery is that you can then use those skills themselves to do particular things because they themselves are directed. Whereas with exploration, you just have a bucket of states, which is all of the states in the world. And you don't really know, you have to like solve a difficult planning problem again in order to figure out how to do things with them.
Mm-hmm.
And so you're like doing some of the like skill learning problem beforehand rather than having to rely on your reward supervision to do all of that.
Got it. And so going back to your setting for this example, you're dropping the robot into an unfamiliar environment, and the robot is given you've specified some set of skills that the robot needs to figure out. Is that stating it too strongly, or?
I think that's a little more than we assume. So what we're assuming is that the robot just has access to the environment. So they don't actually have access to the skills that they need to learn. You just have access to sampling from the environment. So you can interact with the world, but you're not actually told what the skills are that you have to do. And you kind of propose those yourself. So you interact with the world and you try to propose skills and tasks for yourself such that all of the resulting behaviors from those skills and tasks are as diverse as possible. So the assumptions are a bit weaker than what you were mentioning. It's just access to the environment. That's it.
And what are some concrete examples of skills that are relevant to the environment that you're considering?
Yeah. So for instance, we considered a lot of these locomotion environments that folks in reinforcement learning love, right? These OpenAI gym environments. And in these gym environments, we found that you can get agents to run fast forward, run fast backwards, walk slowly forwards and backwards, backflip forwards, backflip backwards, move in different directions, navigate around walls, things like that without any reward functions at all. Put into a different environment, let's say visual navigation, you found that you can navigate to different landmarks and explore, like going to different objects, picking them up without rewards at all either. And so that's kind of the span of skills that we've seen so far.
Got it. And so are your experiments in this area all simulation based as opposed to physical robots?
Yeah, so our experiments in this space have been mostly simulation based, but there's been a cool line of work from some researchers at Google, which have taken these similar ideas and put it on a low cost walking robot. And they've got it to navigate around rooms and like push objects around and things like that, all from unsupervised skill discovery. So I think there's some evidence that it can work in the real world, but preliminary so far.
Wow. You mentioned data collection as one of the things that you're interested in due to its challenges. Elaborate a bit on that problem and the way you approach it.
Yeah. So I think the thing that's often not talked about when we think about reinforcement learning systems for robotics is that the process of setting up an actual reinforcement learning system for a robot is not as simple as dropping the robot into the environment and letting it run. It's a huge amount of infrastructure setup, which is hidden behind the cameras, right? So there's often a setup for state estimation, which is telling you where all the objects are. There's often a setup to provide you rewards in some way or the other, either by programmatic things or the methods that I mentioned earlier. And one thing that's really not talked about is that when you're doing reinforcement learning and learning through trial and error, you often want to attempt the same problem over and over again, right? So you want to put a kettle onto the stove, you want to try it, you want to fail, and you want to put it back, try it again, and so on, right?
Mm-hmm.
But if you just let a system run autonomously, nothing really incentivizes it to like put it back in the same place and try over and over again.
Yeah.
And so what often happens is you have to have a human who's in the loop, picking the bottle up and or the kettle up and putting it back where you want to start it from, or you have a specialized mechanism which resets things. So often you'll see researchers at Google will do door opening, but behind the door, there's a motor which pulls the door back and closes it so that you can try again. But the problem with that is if you've instrumented the world, then why do robotic learning at all, right? You can just you can solve the task just directly, right? And so these kinds of problems make it hard to actually scale up data collection, because you either need to operate in very, very specific environments, or you need to operate in a scenario where a human is constantly in the loop trying to help your system learn, right? Mm-hmm. And so you can't leave your robot to learn for 1,000 hours because you need 1,000 man hours. And so what we've been thinking about is how do we build uninstrumented, uninterrupted learning systems which can, set up their own practice problems. And so we've been thinking about how do we build RL algorithms that don't just learn how to do tasks, but also learn how to reset tasks so that they can try over and over again. And so the idea would be you learn a forward controller to perform a task, but then you also learn a reset controller to try and reset to a different practice problem so you can try it again.
Wow.
Now, but the trouble with that is you don't exactly know what to reset to.
Mm-hmm.
And so the idea that we use is we kind of like try and reset randomly into states in the world. So we say, let's try and pick a uniform practice problem. So something which is random, and then we try to reset into that just by doing exploration. And then by doing so, you can actually explore the world to practice the problem from a variety of states. And that kind of lets you robustly learn how to do the behavior.
Mm-hmm.
And when the
idea being that if you reset to exactly the same state and have the robot do it over again, there's not really a lot of learning that's going to happen. So you need to introduce some randomness in the reset process.
Exactly. Right. So you try to widen the state of it's kind of similar to adversarial robustness from the core machine learning world, right? Where you try to be robust to different distributions that you might encounter at test time. Mm-hmm. It's kind of a similar type of min-max formulation where you say, okay, you might encounter any possible scenario at test time. Let's try and prepare for the worst and optimize for all of them. And what that allows us to do is just drop a robot into the world, indicate what task we wanted to solve, either via videos or images, as I described, and then you just leave it to learn for 20 to 30 hours now, where it just collects its own data, setting up different practice problems for itself, and then you come back and it does the task from a variety of scenarios. And so I think that's a big step towards actually having large data sets and scalable robot learning. If you look at any robot learning paper right now, it's very, very small data sets that they operate in, and not like the ImageNet size data. And I think this is a step towards that.
Mm-hmm. Is this work that's primarily happening in simulation as well?
No, this one's in the real world.
This one's real world? Okay.
Yes. So most of my work is focusing towards the real world. It's just the unsupervised RL hasn't made it yet, but it's going to make it soon. But this is primarily thinking about what are the challenges for purely real world systems. And so it's a paper called The Ingredients of Real World Reinforcement Learning.
Mm-hmm. And what are the problems that you explore specifically?
Yeah, so specifically we've been thinking a lot about this reset free learning problem. So how do we get agents to learn without any resets at all? And as I mentioned earlier, we've tried doing it with this type of uniformly random practice controller, which sets up different random practice forms for yourself, so that you can keep practicing things. But we've also tried more different approaches, which is trying to leverage the fact that often you're learning multiple different tasks together. And when you're learning multiple different tasks together, some tasks can reset other tasks. So let's say you're trying to like put a kettle on the stove, you might accidentally drop the kettle, and then you can have a task of picking up the kettle and putting it back on the counter. If you're learning that in sequence, then it's providing resets for the other task, right? So when you're trying to build a continual learning system, when you're learning multiple tasks together, it's a lot easier to have a scalable autonomous system just by sequencing the right tasks one after the other.
Are there any parallels or results? I'm thinking about kind of some of the recent work into multitask learning and kind of the traditional ML side. I'm wondering if there are parallel results or experiments on the RL side, whether it's easier or harder for an agent to learn multiple things, and task construction. Are you thinking about those kinds of things?
Yeah, those are really interesting questions. I think one really surprising result in RL, which we've been looking into a fair bit, is when you have multiple tasks being learned by the same model, it can often be really hard to actually learn all of them in a single policy. So if you take, let's say, like a multitask benchmark of 50 different tasks and you try to learn them all together in a single policy, what often happens is that different tasks start to interfere with each other. So you're trying to like pick something up, you're trying to push something, you're trying to open a door, and you're trying to do all of these tasks. Some tasks might push the policy one way, another task might push the policy another way. And when they're all learning together, what happens is often these gradients cancel each other out, and you actually make no progress on any of the tasks. And so we had a paper called Gradient Surgery for Multitask Learning from NURPS in 2020, and it kind of studies this this challenge of multitask learning in RL, especially when you have active data collection. Because what happens is when you're learning different tasks, they're canceling each other out, and then you're relying on the same policy to collect data. Your data falls into the cycle where it doesn't get better on any of the tasks, and so you actually never learn any of the tasks at all. And so we kind of found that pretty surprising, because you'd expect that if you just train on multiple tasks, you'd just be able to learn multiple tasks, but the optimization landscape there is actually quite tricky. And so we kind of found that if you do the simple trick of saying that if gradients are canceling each other out, you just project them to not cancel each other out. So you say that project it onto the normal so that you're like removing any part that is interfering. That allows you to scale up multitask learning to solve a lot more tasks without these optimization challenges.
Is there an implication in there that in learning in general in RL, it is we can simplify the information we're collecting and, focus more on magnitudes than directions of vectors or something along those lines and make progress faster?
That's a good question. I think when it comes to multiple task learning, you have to look at the directions as well as the magnitudes, because these issues really only arise when the directions are pretty different, and the magnitudes of these gradients are such that they're canceling each other out. So I think that it's a bit more nuanced than allowing a bit more nuanced than saying that we can just focus on one or the other. Instead, we have to kind of look at how the interaction between multiple tasks plays with the next round of data collection. So it's if they cancel each other out and the next round of data collection is dependent on the thing that cancels it out, then it doesn't really work the next time.
Got it. I guess that's consistent with the title of your paper, which is Gradient Surgery as opposed to Gradient Sledgehammering.
Yeah, exactly. So what we do is we just like tweak it a little bit so that it's orthogonal now, and so it doesn't interfere with the gradients as much, and in the limit it converges to the right solution.
Got it. Cool.
But I think there's still more of an empirical study to be done in how much this is a problem as we scale up to more and more and more tasks and you use more and more complex architectures, because you'd often find that some architectures just work great on these things and others don't, and it's a little bit of a black box so far. Like the best guess that we have is that different architectures will impose gradients in different ways, and so if you're doing that, then they might not interfere with each other. So, for instance, if you have a multi-headed architecture for multiple tasks, then the heads don't interfere with each other, and that might allow you to solve them better. So I think there's a lot more to explore in the multitask RL space, which is like not very well understood.
One of the areas that you've done some work into is kind of the interface between humans and robotic systems. And I'm thinking in particular, this Ecological RL paper. Can you talk a little bit about that paper and what you're looking at there?
Yeah. So I think it's not so much a methods paper as much as it is a paper about phenomena that might exist in real world environments. And so the premise of the paper is that a lot of the problems that we're thinking about in the context of reinforcement learning, so we often think of exploration and reward shaping as a big challenge, or we think of non-stationary reset-free learning as a big challenge. And we develop algorithms to specifically tackle them. The idea in Ecological RL is that perhaps a lot of these challenges are only challenges in the contrived, simplistic settings that we have been considering, and not so much a problem in environments which are more human-centric, dynamic, things that you might encounter in the real world. So, for instance, let's say you're trying to do the task we were talking about earlier, putting the kettle on the stove, right? And if you're in a setup where there's no humans, you drop the kettle and there's nothing you can do, so you have to go pick it up and then try it again. But let's say you were operating in an environment with humans present all the time, like those challenges are much less of a thing, right? Because a human is likely to come in and say, okay, I'm going to pick up the kettle and put it back to a place where you can keep practicing. So in environments which are not adversarial or unhelpful, but instead are kind of trying to be helpful to your learning process, a lot of the learning dynamics can be quite different than we're considering, right? So we specifically think about two types of things in the Ecological RL paper. We think about what happens when you're in dynamic environments, so environments which naturally have stochasticity coming from other agents or from different factors in the world, like humans, or when you have things like helpful agents in the environment, which are setting up the world in a way that makes it easier for you to do things, right? So, for instance, if you're trying to put the kettle on the stove, a helpful environment would put it back in your path so you can try it over and over again. And so we kind of try to formally characterize what dynamic environments look like and what helpful environments look like and how they affect the dynamics of learning, both in an empirical and a theoretical sense. And so we find that often the challenges of non-episodic learning or reward shaping are significantly less of a problem in dynamic or helpful environments. And so it's kind of like a call to the community to think about challenges that actually matter when we deploy into real world environments, because we don't really care about robots in labs anyways, right? And so
so kind of asking the question, are we thinking about the problem quite the right way?
Exactly.
Do you have any, are we at the point where we have real world examples of this effect? A system that shouldn't work but does because we have these human interventions. Do you have examples of that?
Yeah. So I think some examples from our lab, which we've been exploring a little bit, is we've been trying to get a mobile robot to operate in a playroom and clean up a dirty playroom, like a child's playroom. You have a mobile robot going around picking up objects and putting it into a bin or something, right? And in those scenarios, we often find that the robot is very frustratingly missing the objects constantly and not really exploring in the right space. But if you help the robot out a little bit and you kind of put the objects into places that are helpful for it, then it significantly helps with your learning process. Right? And so a lot of those results are still in the works and haven't been published yet. But initial evidence does suggest that just changing the environment setup to be more helpful to the agent when a human is watching, that's just the natural thing that they do. That already makes the learning problem a lot easier. And I think these kinds of issues would happen anytime you deploy a robot into somebody's home. I guess the problem is it's a little bit of a chicken and egg issue in that we haven't deployed robots into people's homes, so it's hard to see these things at scale.
Yeah. Would you go as far as to say that we'd make a dramatically different progress if we loosen some of our assumptions around kind of non-human interference, or conversely allowed for human help or external agent help in RL and robotics?
Oh yeah, for sure. I think as soon as we allow for human help, every problem gets a lot easier. It's just been challenging to figure out what the right medium is to provide that help and how to incorporate it into our algorithms. That, in combination with the fact that we're not really able to operate in natural human environments. So I think it's difficult to put a human into the loop of the robot, because a human has to sit in the lab and supervise the robot, and it's a big pain. But I think if we flip the problem around and we say, what if we put the robot into the loop of the human? So like the human is just doing their thing. But if we put a robot into their home and they were just living, I think the human supervision that would naturally arise is a lot easier for a human to provide, because they don't have to go out of their way and specifically focus on the system. They're just doing their thing. Right? So I think that actually it seems a little counterintuitive, but I think that deploying robots directly into human environments and studying learning algorithms in those environments directly is probably going to help us make a lot more progress than studying things in the lab or in simulation. The tricky part there is how do we prevent these robots from just being shut off because they're inept, right? And so
I was thinking, what's what might be the simplest robot that has enough utility to not get shut off, right? And provide some value.
It's the Roomba, right? It's got to be the Roomba, and I think that might be a great place to start. How do we take a Roomba, maybe with a small manipulation attachment, like a small arm or something, and deploy it in somebody's home? So in the worst case, it does vacuum your home. In the best case, it helps you clean up your living room, right? And so if we can kind of start to have those kinds of systems deployed, I think that would be I think we have to find the right marriage between utility and and interestingness. Maybe? Yeah, exactly. Yeah. It's kind of tricky.
Awesome. Well, Abhishek, thanks so much for taking some time to share a bit about what you're up to. Very cool.
Absolutely. Stuff. Yeah. Thanks for chatting, Sam. It was very fun.